In this video, we're going to start a new topic of differentiation, which is a branch of calculus. So this video is quite simply an introduction to calculus and differentiation, and in the following videos and lessons we will learn how to differentiate. So calculus was developed in the 17th century by Sir Isaac Newton and Gottfried Leibniz, who disagreed fiercely over who originated it. Calculus itself provides a tool for solving problems involving motion and change. So, for example, methods obtained from calculus are used to study the orbits of the planets, to calculate the flight path of a rocket, for instance, and to predict the path of a particle through an electromagnetic field. In fact, calculus can be used to study any situation where a rate of increase or decrease is involved. Now, speaking about a rate of increase or decrease, I suppose something that's closest to home for us is thinking about speed and acceleration. So we'll have a look at a specific example here involving speed. So the following are distance time graphs which describe the journey of a vehicle. Now, you can see from this graph here, it's made up of three straight lines. So we've got one here, next one going along, and next one going up. Now, what this graph implies is that this vehicle can travel at a constant speed. So the minute this starts moving, it's going at a constant speed, it then changes instantly to another speed, stays at that speed, and then changes instantly again to another speed. Now, if you think about if you were in the car and you were going for a drive, that's not actually realistic. The speed increases gradually. It doesn't just go at a constant speed to start with. So maybe a more accurate graph would be something like this. Now you can see that there aren't straight lines now. So we can actually graph it more accurately using curves instead of straight lines. Now, if we want to know the speed at a certain moment in time, so the instantaneous speed. Now, if we to use this graph, that's quite easy. We can find the gradient of a point here, and that's easy enough because they're straight lines. But actually, if we try to find the gradient of a curve, we don't quite know how to do that yet. Now, if we want to know this instantaneous speed at a certain moment in time, it's known as the rate of change of distance with respect to time. So that's what the gradient is, the gradient of a straight line. If we were talking about a straight line, the gradient is the rate of change of that line, it's the change in y and the change in x that we examine. Here we would be examining the change in the distance with respect to time. Now, as I've said, that's the same as finding the gradient, but specifically for a curve like this, if we want to say find what's the speed after 20 seconds, if we want to find this here, what we would actually be finding the gradient of is the tangent to the curve at that point. And finding this using this graph here, using the graph with the curves, could actually be quite a long process, but differentiation provides a much quicker method. Now, differentiation itself, the process of differentiation, comes firstly from first principles. Now, we'll not be using this every time. It's good for you to know this, especially if you're going on to do advanced higher next year. So I'll just show you this just now, and in the following lessons we will learn how to differentiate using a quicker method. So on the graph of y equals f of x here, so that's the curve, A is the point x f of x, and B is the point x plus h, f of x plus h. Now, to find the gradient of the line AB, so this portion of the curve here, what's the gradient of that? we would use our gradient formula. So we want to know what's the change in y over the change in x. So we have y2, that's y2 minus y1 over x2 minus x1 is the formula that you're most familiar with. So we take the y ordinate of point B minus the y ordinate of point A over the x coordinate of point B minus the x coordinate of point A. Now, you can see here on the numerator, we've not got anything which will simplify. We can't expand this or anything. Remember, f is function. On the denominator, however, we've got an x and we've got a negative x. So that leaves us with h on the denominator. So the gradient of AB here is f of x plus h minus f of x all over h. So the gradient of the tangent at A is derived by reducing h towards 0. So the value of h getting closer to 0. So as h tends to 0, this formula here, so f of x plus h minus f of x all over h tends to a limit. And this limit is the gradient of the tangent at A, i.e. f dashed of x, which is actually the derivative. Now we can write this as f dashed of x is equal to the limit as h tends towards 0 of f of x plus h minus f of x all over h. Now at higher level you're not expected to remember that, but as I said, it's good for you to see it just now, just so you see where differentiation actually comes from. So like I've said, f dashed of x is the derived function or the derivative of f of x. And the derivative, remember, represents the rate of change of the function, we've already spoken about that, and the gradient of the tangent to the graph of the function. So again, we've already spoken about that as well. So the three words for differentiation, we've got derivative, rate of change, and gradient of the tangent. So those are three words which should almost be tripping off your tongue all the time. We should just know those. And the minute we see those in any questions in an exam paper or a textbook or whatever, that's you're thinking of differentiation. That's the topic you're heading towards. So just so we look at a quick example using the first principles that we've just seen. So prove that if f of x is equal to x squared, then f dashed of x is equal to 2x using differentiation from first principles. So we'll use our formula that we found in the last slide. So f dashed of x is equal to the limit as h tends towards 0 of f of x plus h minus f of x all over h. Now f of x is x squared, so that's fine, we've got this bit. So f of x plus h must be x plus h all squared, like so. So we've substituted in. Now if we expand that bracket on the numerator, we would get x squared plus 2xh plus h squared. So we've expanded that there. And you'll see on the numerator we've got this x squared and we've got a negative x squared. So again, those will simplify to 0. And we actually have a h in both terms on the numerator, and we've got the 1h in the denominator, so that will simplify to 2x plus h. So at the moment we've got f dashed of x is equal to the limit of h tending towards 0 of 2x plus h. Now the closer h gets to 0, if h was 0 this wouldn't be here. So as h tends towards 0, we would be left with 2x as required, because that was what we had in the question. We were asked to prove that f dashed of x would be 2x. Okay, so that is a quick introduction to calculus and differentiation from first principles.